Assalamualaikum warahmatullahi wabarakatuh. Today, my team and I will present a case study on renewable energy grid management using the concept of computational thinking. In this presentation, I am with four of my friends, Diri Christina Pitupulo, Muhammad Gifarel Arfa Hadi Wirawan, Faik Fadlul Akbar Harahap. So we're going to start from the background about the renewable energy. Power grid is combining renewable energy source like solar and wind with conventional energy systems. However, fluctuations in weather conditions make renewable energy generation uncertain, causing inconsistencies in supply and demand. So this is our problem statement. So number one is predict energy generation from renewable source based on weather forecast. And the second one is balance supply and demand in real time. The third one is store excess energy in batteries or divert it to other uses. And the fourth one is minimize reliance on non-renewable energy source. And we're using our four pillar of computational thinking. So we're going to start from the composition. We got the information that the predict energy generation from renewable source based on weather forecast, balance supply and demand in real time, store excess energy in batteries or divert it to other uses, minimize reliance on non-renewable energy source.
Okay, next we'll be trying to predict energy generation from renewable resources based on its different weather forecasts. So the first thing we'll do is we'll be collecting weather data by gathering key weather informations like sunlight and maybe wind speed and maybe temperature from reliable sources. Next, we'll be trying to analyze past weather trends by first examining previous energy output data to understand how different weather schemes or conditions may impact this generation and the generation forward. Afterwards, we'll be trying to develop a prediction model using basic calculations or machine learning to estimate energy production. Next is we'll be updating with the real-time data after we've gathered the past trends and past data by continuously refining predictions as new weather information and new weather data will be coming in and becoming available. And then the last step is we'll be improving our accuracy on comparing predictions to actual results and maybe making necessary adjustments to the generation or the weather happening right now. Next. Next is about balance supply and demand in real time or right now. So first, there is monitoring energy supply by keeping track of energy generations from renewable sources and maybe traditional sources. Next is we'll be measuring demand and what we need by analyzing real-time energy consumptions across different sectors. And next is we'll be detecting imbalances throughout the weather by identifying gaps between the supply and demands and what we need to accomplish. And then next, we'll be adjusting the distributions by storing extra energy or using backup sources if we need to use backup sources. And then the next one is we'll be automating adjustments by using smart algorithms to make quick and efficient decisions. Next. Afterwards, we'll be trying to store excess energy in batteries or even divert it to other uses, such as we'll be identifying surpluses energy by detecting when generations exceeds possible demands that we already tried to fulfill. And then next, we'll be deciding on storage versus redistribution, which one is better to store excess energy in batteries or better to direct it elsewhere. And then next, we'll be optimizing battery storage by managing storage efficiently based on the capacity and which charge levels. Next, we'll be redirecting energy smartly by sending surplus power to other grids or applications like maybe EV charging or electric charging. And then next, we'll be continuously monitoring and adjusting to by adapting storage and diversion strategies based on the real-time data happening right now. Okay, next we'll be trying to minimize reliance on non-renewable energy source as we'll be relying more on renewable energy sources. So first, what we should do is analyze usage patterns, which we will trying to be identifying which non-renewable energy is usually used most day-to-day by demand. And then next is we'll be maximizing on using renewable resources or utilization by prioritizing solar and wind power whenever it's possible to use solar and wind power. And next, we'll be enhancing on storage efficiency by using safe access renewable energy for maybe later use or the use in the future. And then next, we'll be optimizing on grid distribution by ensuring that renewable energy reaches its best potential when it's needed efficiently and necessarily. And then the last one is we'll be implementing smart systems like using automation to make real-time adjustments and using the more high-tech technology to reduce fossil fuel dependency.
Okay, we go on the pattern recognition. First of all, we must identify recurring weather patterns, such as higher solar output on sunny days and increased wind power during storms to improve energy predictions. And then the second one, we must recognize daily and seasonal fluctuations in energy consumptions to adjust supply distributions more efficiently. The third one is detect patterns in battery usage and energy surplus to determine the best times for storage or redirection. And then the fourth one is identifying when the grid typically shift to non-renewable sources and optimize renewable energy usage to minimize reliance on fossil fuels. Next, we go on the abstraction. The abstraction, first of all, we must focusing on the key variables. Focusing on the key variables means concentrate on critical factors like weather patterns, historical data, and seasonal trends to predict renewable energy generations. And then the second one is simplified supply and demand control, monitor overall energy consumption trends, rather than tracking every individual consumption detail for real-time management. And then the third one is optimizing energy storage and distribution, which means that focus on strategic times and locations for storing and redirecting surplus energy instead of tracking every minor excess. And then the last one, we must minimizing non-renewable energy uses, which means that prioritize the integration of renewable energy without needing to analyze every case of non-renewable energy consumption. Next, we go on the algorithm of greedy energy distribution for grid stability. First of all, we must input the data. Input the data means weather forecast data. Predict solar and wind energy generation based on weather conditions. Current energy demand. It means that provides real-time data on electricity consumption. Then battery storage level. Indicates the current charge status of energy storage system. And then the last one, non-renewable backup capacity. It means that we must specify the minimum required backup power from non-renewable sources. And then the second one is algorithm steps. The first one is forecast renewable energy production. And then we must adjust supply and demand dynamically using a grid strategy. And the third one is enhance energy storage efficiency. And the fourth one, reduce reliance on non-renewable energy sources. And then we go on the algorithm greedy energy distribution for grid stability. And then we go on the third. The third is complexity analysis. The first one, weather-based prediction, pre-processing, ON. And then the second one is balancing supply and demand grid selection, O1 per time step. And then the third one is energy storage decision making, 0-1. Overall, the approach operated efficiently with a time complexity of ON, where N represents the number of time intervals in the dataset.
The next is flowchart. We start to input data, and the first step is weather forecast, and second energy demand, and third battery level, and non-renewable capacity. After input data, we estimate renewable energy output. It's a solar and wind prediction. Second, identify peak and low periods. After that, is renewable energy supply more or equal demand? If yes, we store excess energy in battery. After that, repeat every 2 hours. If no, does battery have sufficient energy? If yes, we using stored energy to cover deficit. If no, we using non-renewable energy. After repeat every 2 hours, yeah. Lanjut, next. Goblok banget ya, tolol. Aku udah bahas ini estimate renewable so. Next. Okay. Next is algorithm. Why is the greedy algorithm preferred over other methods? First, instantaneous decision making. The power grid needs to quickly determine whether to use store or switch to non-renewable energy at each time step, making real-time processing essential. The second, efficiency and simplifies the greedy approach. The greedy approach ensures that the best possible action is taken at each step, and keeping the algorithm lightweight with on complexity. This makes it well suited for real-time application. And at last, we reduce dependence on non-renewable source. The method prioritizes stored renewable energy before considering fossil fuels, supporting the goal of minimizing environmental impact. Next. Okay. Next is conclusion. Conclusion is to effectively manage a renewable energy system and integrate approach is essential. This involves accurate weather forecasting and real-time balancing our supply and demand, smart energy store management, and minimizing dependence on non-renewable source. By identifying patterns in weather condition and energy consumption, the system can dynamically adapt, maximizing renewable energy utilization. After that, maintaining battery efficiency and ensuring energy availability for critical needs. Next. Okay, thank you for all. Thank you very much. That's my group for the presentation. Thank you. Assalamualaikum warahmatullahi wabarakatuh.